Hello pre-calculus students, and welcome to a video on consistent and dependent systems of equations. We're looking at three different situations here with systems, and we already have seen all these before we had Cramer's rule. We have two linear equations that intersect at one point. That's considered consistent and independent. We have parallel lines which would have no solutions, and that's considered inconsistent. And then we have two lines that are actually the same right on top of each other, and that's considered consistent and dependent. And so what we've done so far with Cramer's rule is we found the intersecting ones. So just to look back at the system of two equations that we've already had, we looked at an example of two equations, and we found d and dx and dy, and then we used Cramer's rule here to find x and y. But we had that condition that d could not be 0. So this only will give you the two solutions if d is not 0, because if the main determinant d is 0, then of course you have a 0 in the denominator. Well, this set of notes is about how can you tell when you have a 0 in the denominator whether it's a case where they're parallel or a case where they are overlapping. And I'm not so much concerned about the terminology up here as I am concerned that you understand the kind of ways that the lines interact. Okay, whether they're parallel, coincide, or they just intersect at a point. So we already know that if the determinant is not 0, then we get a solution, and that's what we've looked at so far. But these are the two cases where the determinant is 0. So in the case where the determinant is 0, but one of the other, dx or dy's, is not 0, so either dx or dy is not 0, that's where you have parallel lines. And in the case where d is 0 and so are both dx and dy, so d is equal to dx is equal to dy is equal to 0, if they're all 0, that's where you have overlapping or coinciding lines. Okay, so let's just let's look at a couple of these. Now we're in the directions. We're only asked to determine if we have one solution, no solutions, or infinite solutions. In other words, intersecting, no solutions would be parallel, and infinite solutions would be coinciding. Okay, so let's just look at this first one. So we have a system of equations, and we're going to first look at d, and remember the determinant 4, 8, 3, 6 is d, just based on the coefficients. And so this is going to be 4 times 6, which is 24, minus 3 times 8, which is also 24, so that's 0. So right off the bat, we know that we're not going to have a single solution because the determinant is 0. Okay, so then we look at dx. So dx is, remember when we replace the x's with the solution determinant, so we get the determinant -1, -2, 3, 6. All right, and this gives us -6 minus -6. That's -6 plus 6, and that's 0 also. So far, we could be looking at one where all three are 0. Let's see if dy is 0. All right, so dy is where we replace the answer solution with the 3 and the 6. So we have 4, 8, -1, -2. And this one is 4 times -2, that's -8, minus 8 times -1, which is -8. That's also 0. So in other words, d is equal to dx is equal to dy, and they're all 0, which means we have a case of coinciding lines. Okay, so this is going to be consistent and dependent, like it says over here when they're all 0, and this is infinite solutions. So infinite solutions. All right, let's see what happens with the second one. All right, so let's kind of separate this out. So let's look at d first of all. So d is equal to 6, 5. The determinant 6, 5, -4, -2. And when we multiply that out, we get 6 times -2, which is -12, minus -20. Well, that's not 0. So it's 8, but it doesn't matter. What matters is that is not 0, and so that's the first case, and so we have one solution. We're not asked to find the solutions here. So there's D is not 0, so there's one solution. All right, and let's look at the third case. So this time, our D is 15, -5, and 30, -10. That's a D. That's -150 minus -150. That's plus 150. Minus -150 is plus, so that's 0. So D is 0. Let's see what dx is. So dx is replacing the x with the 2 zeros. So we have 2, 0, 30, -10. So we get -20 minus 0. That's not 0. That's -20. So what we have is that while it's this case right here, while d does equal 0, dx or dy, in this case dx does not equal 0. So we have d equals 0, dx is not 0, so this is a case of parallel lines. Okay, so this is parallel lines. So we would say no solutions would be how we answer that. So no solutions. Okay, that's the two-dimensional case. Okay, so before we look at the three-dimensional case with all of these diagrams of planes, let's just kind of think of what it even means to graph something in 3 dimensions. So I'm just going to show you briefly what XYZ even looks like. So let's take a look at an XYZ plane just so you can kind of see what this looks like. So here's a plane, and here's another axis. So here's like our x-axis, our y-axis, and this will be a z-axis. So you can kind of make this look sort of like a parallelogram so that you can get the sense that numbers on the bottom plane can be graphed. Like, for example, this would be 1, this would be like a positive, these would be the negatives over here, negative y's. So you get this sense that this is a slanted plane, and you can imagine something that's on that flat plane. So a point like, for example, 2, 1, 0 would be over 2 in the x direction, 1 in the y direction, and then it doesn't go anywhere. So this would be like 2, 1, 0. A point like 2, 1, 3 would be the same place, only it would go up 3 units. So you'd have to, and now this is the problem, it goes up, if this is a length of 3 units, this would go up to here. But the problem is you can't really tell on the graph exactly whether that's 2, 1, 2 or 3, or maybe this could be 1, -2, 0. You can't really tell. So this there is a complication to graphing in 3 dimensions, but that's basically how you can plot a point. Now what you're looking at here are entire planes in 3 dimensions, and what you're looking at when you're looking at a system of equations with 3 variables is actually 3 planes. Okay, so you're looking at the interaction of 3 planes. And so we are really asking the same question. So in this first scenario, the 3 planes would intersect at a single point. And you can imagine you're in a room, just look in your room, and look at the wall, 2 walls and a ceiling, how they intersect at a single point. So that's sort of the scenario that we're looking at here. And this is the case, just like before, just like the 2-dimensional case, this is the case where D is not 0. This is where we've already used Cramer's rule. And we've got basically similar things going on here. So we have, except that they're in a different order in this picture. So over here, we have infinite solutions. This is kind of, sorry, we have no solutions. So this is kind of like, if you look at both of these diagrams here, there's no points that are in common to all 3 planes, right? The purple plane and the blue plane on this line have points in common, but there's nothing on the orange plane that's over here. And there's not a single point that's on all 3 planes. So this would be, either one of these would be like a case like parallel lines, but in 3 dimensions, even though it could be parallel or a situation like this. So this would be where D is equal to 0, But one of the other three, dx, dy, or dz, is not 0. So, but dx, dy, or dz is not equal to 0. Okay? And then the last case would be something where there's an infinite number of solutions, like this case here or this case here, that they can all be right on top of each other, or they can have the entire line full of solutions. They're both infinite solutions. So that would be the case where d equals dx equals dy equals dz, and they're all the same thing, which is 0. All of them are 0. The focus here then is on if d is not 0, there's one solution. If they're all 0, then there's an infinite number of solutions. And if d is 0 but one of the others is not 0, then that would be a case with no solutions. Okay, so let's look at a system of 3 equations with 3 unknowns. And by the way, here we have x, y, and z. It's just that y is 0. So when we look at our determinant d, we're going to be making y 0 for that first one. So the first column has x's, and they're all there. So that would be -4, 3, and 2. The y column would be 0, 1, and -6. And the z column would be 4, -3, -2. 4, -3, -2. All right, so let's evaluate this. I'm going to ask you to pause the video and let's just evaluate it. Okay, so the determinant d is 0. So now we're going to see if the other ones are all 0, and we're going to see if there's either, we know there's not one solution. We're going to see if there's infinitely many or no solutions. So I'm going to go ahead and write dx, and then we'll simplify that one, or evaluate that one. So dx, let's use all our space here. I'm not sure how much we'll need. So dx would be, the x's would be -4, 3, 2. That's going to be replaced by 0, 12, -14. So 0, 12, -14. The y's, 0, 1, -6. 0, 1, -6. And the z's, 4, -3, -2. Okay, let's evaluate that and see what we get for that one. Okay, so it looks like we don't get 0 with this one, even though we have a couple zeros here. And that's always fun when you're doing a 3 by 3 determinant and you end up not having to even worry about 2 of the 2 by 2s there. But the last one is clearly not 0, so without even multiplying that out, we know that dx is not 0, so we have a case where they're not all 3 zeros, so it's not infinite solutions like this case. It's just parallel planes, or it could be a situation like this, but we know that there's no solutions, no points in common between the 3 planes that are given, so there's no solutions. Okay, whoops, no solutions. So that completes our unit on Cramer's rule. Hope you found this video helpful.